take a second to run through a good related rates problem, just that discusses a few things that are related to the stuff we did in class and also just expands on that a little bit more. So, I love making, ready mix, cake mix type stuff. So let's say Tasty Mix Company is making this kind of super cool Trader Joe's-esque type cake mix, something, trendy and cool, and also has the none of those nasty things that we get in our food that we assume we get from other supermarkets. So why we think it's cool to go to Trader Joe's. I think it's cool. Anyway, we got this revenue function. Let's say here's our revenue. Let's say that's our daily revenue function for this relatively small company, where X is the number of boxes of mix produced and sold in hundreds. So we got to remember that when we get back to the units later next year. I think I'll make an edit as I make my way through it. So that's all right, but it's not huge. So let's keep going. What if we were to ramp up the production? I mean, wouldn't it be nice if you could do that? Sometimes, you open up a business, you start selling so many. What you're trying to do is either by research or by just experience or just dumb luck, you've decided this is how many we're producing. And if all is going in a perfect world, you're selling everything you produce, well, that's great. Then you have to start thinking, what if we increased production and we could sell those? What would that do for us? So you go and increasing production is a complicated business. So how do you go about doing that? I mean, is it an efficiency you found in your process? Were you able to, just throw more money at it and just make it work? But again, that's a cost issue. We're talking just about revenue. If you decide to increase production and there's a whole lot of cost involved in that, revenue minus cost is your profit. So if you're increasing cost, you're stealing from your profits. But if you're able to increase production without a whole lot of expense, that's when it's pretty appealing. So let's say we can do it reasonably efficiently, 50 units a day. Let's increase production, 50 units a day. From current productions of, let's talk about it. So the idea is if I introduce this 50 units a day, I want to bump things up. What I'm actually introducing is a new variable, time. Because my production or my revenue function right now is revenue in dollars, X units, like number of boxes and hundreds produced. This whole idea of doing something increasing production per day actually means to the problem I'm introducing a new variable. So this is where implicit differentiation comes in handy. We can actually introduce this idea of a rate per day, even though there's no time, no day stamp on any of the variables in here. So what we're going to do is call that increase of units, 50 units per day, dx dt. And the x is number of units, t is time in days. So what we're saying is dx means change in x over change in time. 50 units over 1 day. So next is I want to go ahead and take the derivative with respect to time, and what it does is open up. It allows us to see how this new rate actually affects revenue. Mechanically, you're going to see this happen. So we're going to take the derivative with respect to time of the function. So you can do this anytime. If I want to see how a particular new variable like time affects the rate of change of any variable, well, you take the derivative with respect to time. And then if you happen to have one of some rates of change, what it's going to call on is you're going to need to know rates of change, this new variable. When we put in the differentials, you'll see that we need some information to actually find the rate of change of revenue. And watch what happens. Let's go take their derivative and see what we need to actually come up with a value for the rate of change of revenue. So I'm going to take the derivative of both sides with respect to time. And that means dr dt. And then remember, this is new variable dt means when I run into x's now, even x's, I have to write the dx dt afterward. Because if you run into a variable that's not your input variable, like t here in this case, then you have to write d variable dt afterwards. So, we can take the derivative of our dr dt. Got it? Derivative of 40, that's 1 dr dt, by the way. I'm just leaving off the 1. 40x, the derivative of that is 40. But we're going to put the dx dt afterward. If you can remember when we talked about this in class a little bit, the reason what we have going on, that's a little mini chain rule going there. The underlined portion, that x, is actually our inside. Let's say that's our inside function. Okay, that's our blob. 40 blob to the first power. And when we take the derivative by chain rule, remember we take the derivative of the outside, so we'd have 40 blob now to the 0 power, because we subtract 1, times derivative of blob. So chain rule is always, derivative of the outside with the blob inside unchanged times the derivative of the blob. So x is our blob. Watch this. Okay, so we'd have 40 times 1, because the power comes up front. We subtract 1 from the exponent, so now it's 0. left the blob, our x, inside untouched. But right after we take dblob, derivative of blob, dt outside. And so in this case, dx, dt outside. That's the long and the short. You guys can just remember, just take the derivative like we always do, and afterwards stamp it with d of variable dt. Okay, so that's, and when we do implicit or related rates problems, it's always with respect to time. So it'll always be d variable dt afterward. Take the derivative of the function, put a d variable dt afterward if it's not a t already. So moving right along, that's the inside scoop. If you don't want to pay attention to that, just ignore it. But that's the why and where it comes from. So let's just do the last one straight up. X squared, we know the derivative is 2x. Put a dx dt afterward. There it is. That's your derivative. That's the rate of change function for r. Now the only thing is that is, well, what we're going to do is take and try and find how revenue changes with this new rate. Well, the new rate dx dt, this implicit differentiation stuff gives me a place to put that rate to see how it affects the change of revenue. By the way, this is change of revenue with respect to time. So now I'm going to actually put in the dx dt, which we now know is 50. What I need though is, see there's an x in there, that x variable? Well, we have a place to put in incorporate our new rate. Okay, keep that in mind. Then we need to find this x. We also need the x units, how many is produced. So any revenue that you take in is dependent on what your current production is, because the production rate, how many you're putting out there, actually affects price, because price is dependent on the number of units sold. Demand is a price. Number of units and price are very closely related. That's what demand is all about. So we say, let's say x is 20. That's our current production. We're going to ramp it up 50 units of production per week. So we're currently 20 per week, and we're trying to figure out if I increase 50 units per week, what's that going to do to my revenue per week? So, and that's what's coming up. So dr dt, okay, given that x is 20 and our rate is 50, let's plug them in, see what we get. So 40 times 50, just put the values in where they go. X is replaced with 20, dx dt with 50. Multiply it all out, I get 0. Well, how about that? I just ramped up production for my current rate of 20 units, and I am getting now 0 increase in revenue. My rate of change of revenue is $0 per day. Not real excited about ramping up production. In fact, what's funny about this problem, let's do another one real fast. Let's say, okay, maybe it's because I'm ramping it up too much, going overboard. Let's use 30 for our rate of change. All right, 20 goes in for x, our dx dt is 30, I put it in its place. What's that? Wait, I got 0 again. So here's the issue. I'm going to back this up just a little bit, got a little carried away there. Whoops, stop right there, stop. And notice what happened. I underlined 40, and you see that 2 times 20. At our current production rate of 20 units, you'll see that 40 and that 20, and whatever my rate is, that 30, you're always going to have 40 there, and then 2 times 20 on the other half of the subtraction problem. So whatever my rate is, we're always going to get 0. You notice that? Look in there. For the given production rate of 20, we're always going to get 0 increase in revenue. Now, one, this is a textbook problem that I grabbed from another textbook. Two, that would, if this is true data, we'd be going, yikes. So I kind of think I maxed out my production. My revenue won't go up anywhere from here. Any increase I produce in this won't have any effect. It'll just cost me more money. So I seem to be maxed out. So if this is true data, I'd be done. I'd stop and say, all right, let's keep it at 20 and just go with it. We're not seeing any increase in revenue. We are seeing revenues of certain types. We'd have to look at some other analytics, but that's interesting. So let's try to just back it up. Let's say we go back to production level of 5 units. Okay, so let's pause that here a little bit. And again, I'm going to back that up. I don't know how I got so carried away. Let's do 5 units is our current production rate. So X is whatever we're doing now per week, 5 units per week. And remember, this is hundreds. We're doing 500 boxes of tasty cake. And then we're going to increase that by 15, again in hundreds, so it's increasing 1,500 units. And if I haven't been saying 100 along, I'm sorry, but it's in hundreds. So 500 currently, I'm going to increase 1,500 per week. That's a lot. We're going to see how that affects our revenues. And so let's go check out our revenues. Ready? Put it in there. All right. We got 40 times 15, 2 times 5. Hey, whoa, now we're seeing some business. $450 per day increase in revenues. Hey, that might work. Crazy amount of production I'm putting out there, 1,500 more units, and we're putting out another $450 per day in revenue. hey, if we got this increase in production at a pretty low cost, maybe this is worth it. I could analyze this a little bit further. I have some additional examples on here. But what we just found out is if I have a current production rate X and I increase at a certain rate per day, I can tell you how my revenue changes per day. The idea is this per day business, I needed to take the derivative with respect to time to get the per day. And the derivative of with respect to time, the little dx/dt's that kept popping up, just gave me a place to input this new information of how fast production is increasing, 15 units per day. And then what I get is, hey, my revenue goes up $450 a day. This might be worth it if it's a pretty costly means of increasing production. Fun stuff. It actually is very analytical. It's a nice way to look at, do I want to ramp up my business if it can, get profits going? If we had cost going for how much the production was cost to do it, this would be a more interesting problem because we could say, ooh, I did an increase in revenue, I had minimal costs, my profits went up. Hey, no brainer. I want to implement this change that caused the increased production. If profits didn't go up, maybe you want to think twice about it. Okay, enjoy. Email with questions.